And he came to the United States and worked in various places, including Kitt Peak, Berkeley, Johns Hopkins, and the Space Telescope Science Institute, where you were the deputy director. And he eventually came to the University of California at Santa Cruz, I think in the late 1980s, which is certainly where I first met him, and has been there ever since, working with the UC observatories and as a faculty member in the astronomy department. So Garth has had many scientific interests over the years, but a lot of them have been connected with looking at the most distant galaxies using space telescopes, especially Hubble Space Telescope, and he was involved with the so-called Hubble Deep Field, the Ultra Deep Field, the extra deep field, or extraordinary deep field, and you may ask what can go beyond that, and the answer to that question must be James Webb Space Telescope, and I have to believe that he will be eagerly looking at the earliest, most distant galaxies with James Webb Space Telescope. When we scheduled this talk, we did so with a certain amount of apprehension on some of our parts, because Webb had I think it had just been launched, but we didn't know whether any of the procedures that Garth will tell us about would work as well as he will tell us they have. And so I'm thrilled personally, having had a minor involvement with Webb over the years. Garth has had a major involvement, as you will hear, that this project really has come to fruition in the spectacular way that you're going to see. This is a thrilling time in astronomy, with first images coming probably in June, but Garth will tell us about that. So let's welcome Garth, and he's got a very long title here, which I will paraphrase as Webb Wow.
Yes, right.
Garth.
Thank you very much, Roger. Yeah, my public talk is Webb Comes to Life. I put a long title on it. I said like hell. Make it short. So here we are. So just to give you a sense of this, you've all, I think, seen these images, but basically we've got three elements here: hot side, spacecraft, communications, power, cryo cooler, and control systems, and then of course the cold side, sitting above our 1 million SPF sun shield. And so huge temperature difference here, as you'll see. I'll show you the actual numbers, but just there's a lot of designations on here, but the core parts are those three elements that I just mentioned: telescope instrument, sun shield, and the spacecraft. And of course, whoops, did it jump? So here's a optical diagram just to give you a sense of this. It's a classic three-mirror astigmat and astigmat telescope feeding a set of four instruments, wide field, very high optical performance, and this is all cold too. So these four instruments and the telescope, they are part of the cold system. And the layout in the focal plane is actually interesting in that we can operate these instruments in parallel. And that is very valuable. You know, it's launching a $10 billion telescope here, so all the data we can get whenever we can get it is very valuable. The FGS is grayed out because it's used for pointing and control, fine guidance system, but the rest, cameras and spectrographs, are the four key instruments for the telescope. And so it is interesting thinking about how we point and get to see the sky on this. So this is a rigid body. Their telescope cannot move with respect to any of the components, the spacecraft or the sun shield. So we have to move the whole telescope to see any object that we want to see in the sky. And we can basically see anywhere in the sky over a year period as we go around the sun, and we can sweep out a swath across the sky by rotating about the sun line by 360 degrees. And also, this is where I feel like I need to get on Amazon and get a model and like show people this is what it does. But so we can tilt by 50 degrees as well. So we can do a wide swath around the sky at any point, and then that moves around the sun a little bit on the short axis, but not much. Those are the two major motions that are used to find sources. So, Christmas Day morning, we finally got to the launch pad. So 7:20 a.m. was the designated launch. There were, at Space Telescope Science Institute, where I was that morning, where Wendy and I were, these lovely cookies with each of the science themes laid out on them. If you look at the ring around there, the core science themes for Webb are laid out on that. Anyway, so 7:20 a.m., the mission control manager pressed the button and it went exactly on the dot. That was when it was scheduled to go, and it went. And it was an astonishingly flawless launch. As we were watching the screens, I'm sure many of you saw this as well, the French control manager, flight control director kept saying nominal, and we'd all go, yay, verily, it's going great. So this nominal kept coming up all the way. This is good news for anybody watching space missions. It's the right word to hear. So when we got up there at the end, and the telescope is sitting on the upper stage, we were waiting to see what the onboard cameras would show us. So ESA had set up some cameras on the upper stage looking up at Webb. They weren't intended to be on the Ariane 5, they were actually set up in 2019, they were planned to go on the Ariane 6, but ESA brought them forward, so the first time these cameras were actually used on the Ariane was on this mission. And they show the spacecraft, they show Webb moving away. So that we actually got to see Webb separate from the Ariane 5 upper stage. Before this, Ariane 5 upper stage had been rotating like a chicken on a spit to make sure that Webb didn't get too hot in the sun on any one location. So it was tilting back and forward like this, and then we got to the point where it was time to release Webb. And so it was released, and the camera was showing Webb moving away, and we were listening to the commentary from Flight Center in Kourou, and the guy was saying, well, in 6 minutes we should have the solar arrays come out, and we probably won't see those. And so we're looking at it going, oh, it would be nice to actually see them. But meanwhile, Webb is sort of drifting away here, and then I think, no, I can't speed this up, I'll screw things up. So we were waiting there for just to see what would happen, you know, whether it would just disappear from view, because of course the upper stage and Webb were going to diverge. We didn't want the upper stage following Webb out to L2, that would not be good. And so the plan was to diverge it. And so we were all going, oh well, so sooner or later it will disappear from view. And then suddenly it started, the solar array came out. And the commentator said, huh, that's early. And we were all scratching our heads thinking, wait a sec, this was only a minute or so, what's going on here? And so this, the array came out, and we all sort of, those of us in the room turned to each other and said, what happened here? Well, as long as it comes out, that's good. This is crucial. We only have a few hours of life on the batteries. We have to get this array out quickly, but this was really quick. So the array came out, and we were delighted with that change, but we didn't understand why. I saw the system engineer for Webb, who spent 10 years working on, and I turned to him and I said, what happened? Why did the array come out so quickly? And he said, beats me. So it turned out the launch was so flawless that Ariane put us in the right position to go to L2, and they rotated it back and forth to keep it not cool and not get hot in any place. They let it go at exactly the right orientation and velocity. And the onboard software was monitoring this, because this was an autonomous release. It was about the only autonomous release we did on this mission. And it went, oh, I'm in great shape. Let's deploy the solar array. And it did. So it took a few hours before I finally heard that was actually what happened, that everything was in such good shape. So anyway, 29 days of, and you saw a lot of stuff in the media on this, went through all these amazing deployments, getting the sun shield out, the telescope set up and all. So there were 50 major deployments in this 29-day period. There were 178 of these non-explosive actuators that were single-point failures. There's something like 300 single point failures overall. They all work beautifully, of course, because we have a spacecraft, a mission now. There are 132 little actuators that have to move the mirrors out. And these actuators have to move 12 microns, and they can move 7 nanometers per step. These are incredible actuators, but they all work too. So at day 29, Webb was inserted into L2. And so, oops. I'm not sure what I can do here. Yeah, let's try that one. So at that point, so in that 29 days, Webb had gone out the 1.5 kilometers to L2 past the moon, and it had done 2 critical burns on the way. So Ariane, of course, had to inject us into the right approach to L2, but it couldn't inject us too fast because there's no way to slow Webb. So if you are going too fast, you overshoot L2, we ain't going to get back to it. There is no way to do that with Webb, with the way it's oriented and with its propulsion system. So every burn had to be just a little bit under what was needed. Ariane put us remarkably close to what was an optimal underneath, as it were, in terms of velocity. And so when we had to set up and do our first onboard propellant burn to help us get to the right place, we didn't need very much fuel. So originally the mission was said to be 5 years, lifetime, goal of 10. And that was going to be limited by the onboard fuel. It turned out when they did the burn for MCC-1A, they thought, wow, we didn't use much fuel here to get to the velocity we needed. We're going to do a lot better. And so it wasn't said for a while, but in fact we have over 20 years of life on the fuel on board. So from a fuel perspective, Webb could last 20 years, which is amazing. It was far more than we thought we would have. Another little burn, and then finally there's a burn that put us into our halo orbit around L2. So we're in great shape from the perspective of lifetime. So now that we're in L2, and of course going out there, there's a huge range of activities in this 6-month commissioning period. And I just wrote them down here. There are some 700 odd high-level activities that have 10,000 steps in there with, and after the 29 days, there are about 7,000 remaining. And so this has to go very rigorously, piece by piece, through this to set the observatory up. Now, mirror segment phasing and alignment is a crucial part of that, and I'll show you that, and also checking out the instruments. So we're now well into the 3rd phase up there, the instrument commissioning. And so just to give you a sense of the temperature ranges we're dealing with here, so we have this, as I mentioned before, the hot side and the cold side. So the hot side is sort of room temperature up to boiling temperature potentially on the sun shield, and 40 degrees Kelvin on the other side is basically the design goal there. And these 2 lines to show actual temperature measurements on the hot side and the cold side over the first 100 days. I'll show you a better figure in the next slide where you can actually see this more clearly. So you'll see here that there's a group of lines that run down to 40 degrees K, which is sort of our focus, our operational design goal, and it's got there beautifully. Then there's one which is very different, and that's the mid-infrared camera. It needs to be colder. The near-infrared cameras can all run at about 35, 40 degrees K. They work fine at that. So MIRI, though, the mid-infrared instrument, needs to be at 6 degrees K. And that is the only active cooling on this whole observatory. Everything else is done passively, cooling to the universe, to the 3 or 5 degree K, whatever it is, equivalent background from the zodiacal light, etc. So MIRI has this active cryocooler. We have to be very careful about the temperatures in the instruments at various points in the cooling to make sure we didn't get any water ice buildup, and particularly with MIRI. And so there are heaters and a lot of control of that done. So it wasn't until late in the game that we were confident that we could start letting MIRI cool down, but as much of the contaminants that we were worried about had gone away. And the cryocooler was turned on at that point, and then the cooling MIRI temperatures dropped very rapidly after that was turned on, and that worked beautifully. It has a two-stage process, and so there's a complicated pinch point transition which occurs at 15 degrees K, which everybody gets a little nervous about. That worked fine. So MIRI is in great shape. All our instruments are operational, and here is the temperature of the primary mirrors. This is actually, as of mid-March, I didn't update it because they're only 1 or 2 degrees K cooler now. You'll notice they're not all the same. There's some warmer mirrors near the bottom and colder at the top. It doesn't matter. They're all beryllium, and they're very stable, and they don't change shape over these temperatures. So once they're set up, they're pretty much temperature independent. So we have a great, what do I like up there at the top? I don't know if I can remove that. That looks like a zoom thing. I'm afraid we might be stuck with that. I can't see how to easily change that. So the secondary mirror is in that top corner there. That is actually at 39 degrees, and that's one of the coldest parts of the telescope. Yeah, sorry about that. It's not obvious how I deal with that. So here just is a way you can actually check yourselves. Every day they update the temperatures through this web page. And so you can see in Kelvin or Fahrenheit or whatever you want here, what the temperatures on Webb are. So at this point, the activity, once we're in L2, the key activity was making this a real telescope. And that means getting all the mirrors to work together. But that meant also finding where the mirrors were pointing. When you first go up, there's 18 segments that are potentially pointing anywhere. Of course they won't, because there's a lot of engineering and testing done to try and get them in their basic position after they were moved up in the first 29 days. But to make sure that we picked up each of those mirrors, did 156, I think, NGST images in a big scan, the size of the full moon, to make sure that we could find each of those individual mirror images. He did a much bigger area than it turned out we needed. The 156 images were designed to make sure we captured them within the instrument, within the center array. In fact, they were in that small area in the center. So within a week or two of, getting into L2, we had the individual mirror segments, and then they identified each one by tweaking it. And so at that point, we knew where the segments were, but of course the image quality was still poor. And there was a pupil image that was also taken showing just the one segment that was set up on the star at that point. And the next step, of course, was then to try and get these more aligned. And that means two things. One, that the individual segments needed to be brought into tilt. We have a 6 degree of freedom capability on each segment. Tilt them and so on, line them up with the secondary, so making them a good telescope in its own right. And so that was the work that was done on the right-hand side there. And once that was done, we could bring them all together. Now at this point, they're stacked. The mirrors are not phased, so it's still 18 individual segments, 1.4 meter telescope, diffraction limited telescopes. So then there was more work involving a very careful series of measurements with slightly out of focus imaging using the camera lenses to do that. And all the images then came together beautifully, amazingly well. The requirement is diffraction limited at 2 microns. In fact, it's probably a little better than that, but we still don't finally know because we have finished tweaking it across the field and testing a lot of stability aspects. So it certainly meets the requirements that we have a diffraction limited telescope at 2 microns. This is a 30-minute image, and it's showing galaxies. So this is the first image that shows some of the first galaxies from Webb. So this is pretty good. Of course, the quality is not all that good because they only release a PNG. They wouldn't give us the real data. We have to wait. But anyway, at least we could see that there were galaxies in there. And of course, the colleague in Denmark put this together showing a Spitzer Space Telescope image 3 hours and what we could see from this sort of PNG image comparison, and Webb looks a little better, I would say. And only 30 minutes. It is going to be a spectacular telescope when we get real images. And then, of course, with the camera, you want to check the optical performance and characteristics. So here's the pupil image of the whole mirror, of the fine phase mirror, beautifully smooth illumination. So another very nice activity there. So we now about moving into science operations, probably late June that will actually start. And we will see from NASA some good images, probably, I hope, in the mid-June-ish time frame of galaxies and whatever else. They always like to do a spectacular set of early release observations, and they never tell anybody what they're going to do. I have no idea what they're going to do. So we'll have to wait and see. Hopefully they will touch on some of our core science goals here. One thing I wanted to say, particularly for younger folks, is, when you hear about these missions, there's thousands, probably 10,000 technicians, engineers, managers, small business, people have worked on this. But there's absolutely a crucial role for a continuing core group of scientists. And so if you're interested in working missions like this, there are ways to be involved. And this is the group that has been at Goddard Space Flight Center, in many cases working on this mission for 20 years or more. And so it can be a fabulous career path if you really like to get into dealing with technology, with big missions, with challenging, balancing science against the capabilities of the mission. And these are the folks that have really played a major role in doing that. Okay, so that was a status report. So how do we get here? So we're going to be talking about the Next Generation Space Telescope, which was what Webb was called before 2002. And that name changed when the contract was awarded to TRW, which was rapidly bought out by Northrop Grumman around that time. So this is what we were talking about back in the late 1980s. The Next Generation Space Telescope, coming up with a concept. And so these are the words that pushed us, a few of us, to start working on this. Start working on the next big mission. It will take a very long time. Well, let me just show you who said those words. So this was Riccardo Giacconi, director of the Space Telescope Science Institute, where, as Roger mentioned, I was at the time as deputy director. So Riccardo came in one morning and said to me, you need to start working on the next mission. This was years before Hubble launched. We were up to our eyeballs with problems with Hubble, as you can imagine, a few years before launch. And so I said, no way, we can't do that. We've got so much work to do on Hubble. And he said, look, trust me, I know. I've done this stuff, and I know it's going to take a long time. And if you want a mission that follows Hubble, you've got to start working on it now. And Riccardo being Riccardo, and also being the boss, we sort of said, yes, sir. And a few of us got together and started to think about this. And really what we focused on was this, doing a big infrared mission, 8-meter-like scale, passively cooled, well away from Earth. And we sort of came up with that because we knew it would just be a dramatic step beyond Hubble. We had no idea really what we did have some thoughts about the science, but very little. But we knew it would just open up a discovery space that was immense compared to Hubble. And that's what you need if you're going to do the next big thing. And so this is what we were working with, these very somewhat simple concepts, conceptualizing what comes beyond Hubble, before Hubble. And this is, where you're often going to be with doing projects of this scale. These are 20-year, 30-year projects. And we had a wonderful engineer we were working with, Pierre Belli, who was just great at coming up with capabilities here. So here are the key people involved. Riccardo Giacconi. Riccardo, of course, got the Nobel Prize for his work in X-ray astronomy later. Pierre, the engineer, and then myself and Peter Stockman were sort of, and Chris Burrows, another person at the Space Telescope, were sort of the key players in this. And one of the things that we really did after spending some time on this was bring together a community group in a workshop and the Next Generation Space Telescope. And so we said, let's do some big things. We got NASA involved, who told us, we're going back to the moon in the early 90s, so you've got to have a telescope concept for the moon. So we said, oh yeah, right. Being skeptics as turned out to be appropriate. But still we started talking about 16 metre on the moon and 8 metre in orbit. But 8 metres was really what in orbit was what we thought would really be the telescope to work for on this. We also brought this into the decadal survey process and talked about it in the panel that dealt with space telescopes. And we talked there in particular about, we sort of felt we needed to be a little more realistic as quotas it were. Talked about a 6 metre telescope. And we actually tried to cost it out. And we came up with $2 billion, launching in 2009. In current dollars, that was 3.3 in 2009 or 4.3 now. That was actually a pretty good estimate, I have to say, particularly given the numbers that were talked about later. But anyway, so there was another step in this process. It wasn't selected for the decadal survey. There was much more focus on getting CERT going. It was a little beyond. It wasn't quite ready yet. But it was good to talk about it, to get people thinking about it. And of course, we were doing technology development. So NASA headquarters was running a program called Astrotech 21. And Astrotech 21 was really looking far to the future. It was a nice program that they were doing at that point, run through JPL. So we assembled a bunch of folks again to talk about large telescope well away from Earth, passive cooling, and to see what the big technology challenges were going to be, of course, which we knew were many. So the next step in this process came with a report that was put together called the HST and Beyond study in the mid-90s it came out. And it looked at, as the title says, HST and Beyond. So it's looking at an IR telescope, interferometers, HST future studies, etc. And so, very nicely written report, but it recommended a 4-metre telescope and with rather simple instrumentation. And it was interesting that when this recommendation came out, Dan Golden was the administrator of NASA, and he was at an American Astronomical Society meeting. And he stepped up and the meeting and was giving a presentation, and he said, I see Alan Dressler here. All he wants is a 4-metre optic that goes from half a micron to 20 micron. And I said to him, why do you ask for such a modest thing? Why not go up to 6 or 7 meters? And I went, yay, verily, this is what we really need. So Dan Golden was the administrator, and so folks took that to heart. Ed Weiler, at that time, came up with some funding a little bit, asked John Mather at Goddard Space Flight Center to assemble a group and do some studies. And then Dan had sort of thought more about this and thought, why not go for 8 meters? And I thought this was absolutely crucial. It was a serious mistake to start out at 4 meters, because when you run into trouble, you end up de-scoping and you get a smaller telescope. I thought 4 meters was too small for the science already, and I sure didn't want to go down from that. And remember, Webb started out, or NGST started out in the next decadal survey at 8 meters, went down to 6.5, so the inevitable de-scope, as it were, happened. So I think Dan Dolan really saved our day with regard to Webb. So we ended up with a telescope which I think really can do the science that we sort of thought originally we really wanted to do. So later in that decade there was an effort then to bring in companies and to develop the concepts much more. And by now the thought that deploying optics and other capabilities was going to be needed and could be done, given experience with some earlier space missions, not of this class or not as challenging as this, but deployments were possible. And so this was a very important study that Pete Stockman edited and put together. And then of course the decadal survey came out and recommended an 8 meter. And NASA had already set the stage for this by Ed Weiler signing what is the Formulation Authorization Document, the FAD, which formally commits NASA to get into phase A. So that combination of the decadal survey and the FAD being signed really started the NGST on its track to being built. But the next decade has its problems. So let me just spend a little time on the science, because it is interesting thinking about how the science case develops for these missions, and it's absolutely central to being able to sell this to the community, to interest Congress, and a lot of people. So, of course, if we go back into the 80s, one of the things that fascinated me when I went back and looked at this a while ago was that we were already talking about searching for Earth-like planets back in the 80s. We had not discovered a single exoplanet, but it was part of the agenda, and we knew what we would need to do, which was a very big infrared telescope. We were talking about pushing out as far as we could. So this is to look at distant galaxies. There was this wonderful idea of looking at the three-dimensional motions of galaxies and nearby clusters of galaxies by looking at the bright stars. And this came up with just not from the group who was working NGST, but from other people who were involved in this. So the range of science was actually, in many ways, familiar when you think about what we are trying still to do with this. Distant galaxies. Star formation is a big deal. We're interested in the characteristic populations of stars and galaxies, and of course, detecting planets and working on exoplanets. So the naming has sort of changed, the details change, but many of the broad concepts scientifically are still there. So what really changed for this particular mission in terms of defining a scientific framework was this field. This is the Hubble D field that was done with Hubble in the mid-90s. I think nobody expected this to be as dramatic as it was in terms of the number of galaxies. This was a 10-day image done with Hubble, and this really set the stage for having Webb be thought of as early galaxy science. By the way, Webb can do this in a few hours, which is pretty amazing, actually. So it would be nice to have that done. We'll do that comparison. So during this time frame, of course, the HDF then had been done, and each of these groups that was working up discussions or volumes on this or reports, of course, wrote science cases for all these, and they were remarkably similar in many ways in the way they overlapped. But they were all crucial to set the stage. We have to be able to have a very strong science case when you go to Congress policymakers and ask for the amounts of money that we are asking for here. But basically, the science case largely got focused around that first stars and galaxies for a long time. The HDF did that. Also, as some people have rather cynically said, if you're going to talk to a congressman or their staff, you have to have an elevator statement. You know, you've got 5 seconds to tell them what it is that you want to do, or you should better be able to write on the back of a postage stamp. So, first stars and galaxies was a good goal, and that could resonate, and you could expand on that beautifully. But of course, Webb is an observatory like Hubble, and it will do an immense range of science. So, just to put this into the current context, here are the basic science goals that have been used to sell Webb now for many years. But no, it's a shame that overlies that at the top. But anyway, one of the things that I have always felt is crucial too is that any mission that you're going to spend the sort of money on that we do on Webb, Hubble, or anything else, better be able to open up discovery space in a whole new way. And so there's got to be discoveries that can be made here. We've got to be in the land of the unknown unknowns, trying to, what are we going to see with this? It's going to surprise us about the universe. And can we reasonably expect to do so? And in a mission of this, or in a telescope of this capability, absolutely. May not happen immediately, but I expect that we will get to see some rather fabulous things here. So, one thing that I also is very important that we've realized over the years with these big missions, that you have great science goals, but you have to make sure that the community of scientists is equipped to actually do that, has the resources it needs, has the data it needs, has the right level of data, has the sort of archive capabilities and all, the software to handle the data. And so Matt Mountain at Space Telescope, director at that time, decided that he really wanted to set up a committee to look at this and to think about this. And we actually met for 8 years deliberating on what would be the best way for Space Telescope, Science Institute, NASA to be able to support the community and to have the capabilities there to make sure we can get the science out quickly and effectively. Because, you know, we have got a $10 billion program here. We have to use it efficiently. So it was a great committee that was assembled. That's John Mather there on the right, you know, future Nobel Prize winner. Actually, he was Nobel Prize winner at that point, not originally. So very good committee of people thinking about various aspects of this in this broad charge of, you know, what do you do to maximize the science return from a mission of this scale. And that's quite an investment of effort. A lot of money has been spent in setting this up so that when the first data comes down, people can get it. They have tools to actually use it, and they're getting the resources to be actually doing that. And so there are a lot of aspects that we dealt with over that time, but it was a very important element. So, and you know, at this point I would say, first slide is a key goal here. And so are we going to be able to actually get to this? It's particularly challenging, actually, when you go through the numbers. So it's not clear how we will go on this. So I'll just quickly show you a slide from an old talk, which shows you the star formation rate density in the universe as a function of redshift. So redshift 10 is about 500 million years after the Big Bang. And redshift 10 is about the start of reionization, as Planck telescope has shown us, and that extends to our redshift 6 about 1 billion years after. So with Hubble, we've been mapping through about 400 or 500 billion years from the Big Bang, which is pretty close to first galaxy period. I mean, we're looking back through 96% of all time at that point. Very little of the universe's mass in stars is built up. At 10, only about a 0.1%. So, in a way, you know, we're already encroaching upon Webb's territory, but this first part is absolutely crucial, and it's extraordinarily difficult. And it really needs Webb's capabilities to do that. And so, I expect that we will push into that. We will find more galaxies like this. We will find this is unusual. This is really dry. So this is another one of those what is going on here results. But it's only a case of one. With Webb, and this was done with Hubble, with Webb, we will get dozens, hundreds of these galaxies, no trouble at all, in some of the early observation. In fact, there was also just recently another galaxy. So I wrote this back, probably the most distant confirmed galaxy until JWST flies. And then a few weeks ago, this one popped up. So we shall see who is right here on both of these galaxies. But there's an awful lot to be learned here, and a lot of information that Webb will fill in. So, I mentioned this before, how little in some ways the science goals actually evolve with time. That the details evolve greatly, but the broad framework has actually stayed very similar. And we've always kept in mind too the fact that we really want to be able to open up the discovery space, and Webb will do that incredibly well. So, let me now talk a little about the challenging periods here. So, Webb started out with a lot of problems, and problems that were really budget related. So how did we get here? Slowly, painfully, and at great expense. But one of the things that I've been incredibly impressed with is the quality, the capability, the experience, and the dedication of the engineering, technical, everybody who involved in this mission that has actually made this happen. So, 2002, when the prime contractor was selected, went into phase B soon after. Basically, Northrop Grumman took on the prime contract for this particular mission. But the next 8 years or so were very rocky. And so Mike Griffin, who was the NASA administrator that came in when Sean O'Keefe left over the Hubble sort of fiasco and going back and revisiting Hubble, realized he had inherited a real problem here, that it was dealing with a very undercosted, as he called it, mission. Every year, the budget had to go back to Congress and tell them that the budget was in bad shape, work was not being done, and so there was a long period of just, I think, frustration from the perspective of both Office of Management and Budget and on Congress on what was going on with this mission. It was approved, there was a lot of good technological development, but every year was a problem with the budget. And so by 2010, this had got very serious. And Senator Mikulski, who was in Maryland, the senator from Maryland, who was a strong supporter of Hubble and of Webb, and I think not just because Goddard Space Flight Center was in the district, he really liked these telescopes and what they did for the nation, for STEM, for just bringing people's, strengthening their links to develop technology and capabilities. So she wrote to the administrator, to Charlie Bolden, asked is sort of in quotes, to set up a committee to look and tell them, NASA, what was going wrong with this mission and was it ever going to launch, basically. It was a pretty direct comment, and Charlie, of course, responded and said, yes, we'll set up a committee to do this. So we looked into it, and we spent not all that much time on it going through, but it was clear that this mission had really serious problems. We wrote the report in a way that was very forthright, and I think, was critical of NASA and what had been done. And my view that it was absolutely essential that this be done in a way that people pay attention to it, because Webb was on the knife edge. A lot of people kept thinking we don't want a superconducting super collider activity here where we spend billions on a program and then it just gets killed. So there were a whole lot of recommendations. Some of the core ones are we must, everybody must, NASA, Congress, OMB administration, must understand what this mission is actually going to cost. And you must give it the reserves it needs every year to function effectively as a program. And really, this is important enough to NASA that you have to take it out of the science area and report it to the administrator. Make it clear that the administrator's office thinks that this is crucial to NASA to be successful. So NASA did all these things. So why was it that things went so badly wrong? Well, the budget was too low initially. There's no doubt about that. Every year there were not enough reserves to deal with problems, and that was crucial. The challenging new technologies were being developed while this mission was underway through phase B, which is getting a bit late for some of those. But the absolutely crucial thing was this sort of combination of lack of reserves and deferral of work. This is not something I had much experience with, but the project managers, all of whom on this committee, everybody else is a project manager except me, really understood these missions and said that, if you get into a situation where you don't have the reserves to deal with serious problems and you defer it, you're likely to see the cost of that particular aspect grow by a factor of 3 at the point you can come back to it, you have the money to actually do it again, typically. And that's a huge impact. And so they said you absolutely must have the reserves so that you can deal with problems when they arrive and you can manage the program effectively and smoothly. And so we also did a rough budget estimate and came up with something like $6.5 billion and launching a few years later than what NASA said, and asked NASA to do a very careful analysis. Sorry, it's just, okay, so support this, in many ways this did not make OMB and Congress very happy, but NASA took it to heart and came back with new cost estimates. And they did that fairly quickly, in about 4 or 5 months. And in 2011, early 2011, they said that it was going to cost $8 billion and it would not launch until 2018. This was a huge change from a congressional perspective. So everybody was unhappy, especially you look at it, I don't know how easy you can read that, but that's sort of $500 to $600 million needed every year to fund this mission to get it to launch. That is a lot of money. And so that was what NASA now was saying to Congress, and unfortunately, the reaction was, we're going to kill it. So Chairman Wolf and the House Appropriations Committee said, no, this is too much. This mission's running way over. Poor management, billions of dollars over budget, let's kill it. So they had to go undertake a large effort to now get this back again. And there was no guarantee this was going to come back, even with Senator Mikulski's support in the Senate. And so we actually got a lot of support from laureates and also Nobel laureates, but also a lot from physicists who realized and remembered SSC and said, we don't need this to happen again. It may not be our mission, but we recognize the importance of big projects and they've got to be able to go ahead. Unfortunately, we had astronomers who were going around saying, oh great, let's kill it and we'll use the money for something else. It was incredibly naive. You kill it, the money goes off to some other area. It's CJS, it's science, justice, and commerce. And everybody else, in those various committees is going, oh, extra money for us, not for science. So killing it would not have done good for science. So there had to be a big effort both in sort of educating and trying to help Congress understand, but also countering all the attacks we were getting in the community too, which wasn't good. One of the things that I think absolutely made a difference here was that Webb was already on the public radar, and Webb was interesting enough to even teachers and school kids around the country, lots of folks in planetary amateur astronomers, planetarian visitors, and they were writing to Congress. I mean, I even got, as I said here, an email from a teacher in Kansas saying, what can I do to help? And I thought, wow. This mission, is years away from launch, but it's already captured people's imaginations. So fortunately, by the end of the year, about 5 months later, Wolf and Mikulski negotiated in conference and sorted out what to do here, and the mission came back again. So this was an incredibly challenging time and also a learning experience about what to do with regard to these programs. You've got to develop support. So at this point, with the growth in the budget and a much better structure to doing the program, things could go now in parallel at Northrop with the spacecraft and the sun shield, and all the work could be done on generating the big mirror, putting the mirror together and then testing it. The testing was an absolutely crucial part of this process. We really needed to make sure that we tested the cold optical system and that we tested it fully through into the instruments. So Webb, we never did this with Hubble, and we had this horrible optical problem that we didn't realize until we got into orbit. Couldn't afford that with Webb. We can't go back and service Webb. We have any problems, that's it. So we had to make sure that this worked, and it went down to Houston to a giant chamber down there that was set up for the Apollo astronauts. And it was there for several months cold, undergoing tests of all the instruments and the optics. Unfortunately, it was Hurricane Harvey, was it? Yeah, that whacked Texas right in the middle of this activity. And there was 3 feet of water around Houston, Johnson Space Flight Center. And so no supplies could get in. Anybody working on it was stuck sleeping in the control rooms, etc. And there was a major problem. We needed liquid nitrogen to keep the system, the tank cool. And one of the engineers down there managed to find a company that was prepared to bring in a truckload of liquid nitrogen through 3 feet of water. I thought that was pretty gutsy of the truck driver actually to do that. And it was good they did that, otherwise we would have warmed up and lost a bunch of time. So this test was really successful. So Webb did this one really right. That we knew that we had a good optical system and good instruments going. And you'll see I just quickly brought back this chart which shows the cooling curve that was done in the tank there, whoops. And so, we took it down to the 40 degrees K or so. Tank had liquid hydrogen and liquid helium to do that, and did all this testing at temperature that it was going to see in space. So that was a crucial test and very effective. So at that point, Northrop was out working on the sun shield and on the spacecraft. And so here is this sun shield. This is an incredible technical, I think, challenge and success. So this is these flimsy layers of what we've put up in space with tension and are keeping the spacecraft cold, keeping the telescope cold. And in some ways it looks easy, but I would say this is the greatest engineering challenge that we face in this mission, dealing with 5 layers of floppy material like this and being able to roll them up and deploy them, which we did and did very well. So here they are, all expanded in the clean room at Northrop Grumman. And of course, you can see up there, large numbers of release mechanisms, of single point failures galore up here, huge number of cables. I saw the full-size engineering model of this and I was astonished at the cables running all over the place. And thinking, whoa, we're going to be pulling on these cables in orbit and expecting everything to come out and to deploy and tension properly. And so they did, but I think there was always a hint of uncertainty and nervousness from everybody who had been involved with this watching it. So then 2018 comes and 2017, 18, and we start having problems again. Screws are found on the floor after some environmental tests. The thruster valves were leaking. And so the optical system had actually come together very well and had gone out to Northrop, but the system at Northrop, the sun shield and the spacecraft were not going well. So here is just a quick image of the two parts of Webb that ultimately put together. So that structure in the middle of the sun shield was taken out, of the telescope was put in. And so this caused another committee to be put together to do an evaluation. And of course, it was going to cost more money, a couple more years. And so at that point, Congress was pretty unhappy, but we'd already spent $8 billion on this, so they went reluctantly, just signed off on it and agreed to go ahead. Interestingly, this is a time where there was a transition at Northrop. And what happened was that NASA decided that, and with agreement with Northrop, that they would put a team of engineers and people in at Northrop. And so now we had 2 groups working at Northrop who had very different cultural backgrounds in many ways with how they did space missions and a different experience. And they integrated and worked extraordinarily well. And I think the change was, the change in the way things came together was really apparent to folks watching this, that things worked better, there was more questioning of what was done and cross-checking and so on. So the next couple of years went very well. And of course, we got the complete system up at Northrop and the last deployment. Everything was looking great. And then we took it to Kourou, shipped down to Kourou and launched. And so we now have, and we're at the point now where we're checking out the instruments. There are lots of little detailed things that are happening that need to be worked and so on, but Webb looks great in all aspects. It's going to perform even better than we had planned, I think, with regard to its optical performance, and the instruments are looking great as well. So I think, we're starting a new era within a couple of months when we start getting science data coming back, and a lot of that data will be public, and so will be available for anybody to look at and work with. A lot of it is going to be proprietary, which I find frustrating, but it's just the way it is with this particular mission. But there's enough that's going to be public that anybody can have a look at it and see and think about what they would like to do when Cycle 2 comes up at the end of the year. So we're there, almost, and I think effectively there from what I've seen. So we have a telescope. So thank you very much for putting up.
Wow. So thank you very much, Garth, and congratulations to you and all of your colleagues. We've had 10,000 people who really put so much into this over a long period of time to stay with it. It's going to be great. I think you've made that case. Perhaps I can just ask the first question.
Sure.
Dream a little of the science. What is it that you hope to see? Be specific and say something that you choose. We won't hold you to this, but
You know, I've got to see the build-up of those first galaxies. I just, you know, we've been talking about this for 20, 30 years. We've been looking at Hubble data. We've been working, pushing back. Oh, it's hard work. And with Webb, it's going to be pretty straightforward to take a big step in terms of going back that sort of few hundred million years. So I, you know, really want to see those deep images and pull out those faint little objects and characterize them and put them on a figure like that and say, oh wow, this is the time scale that, you know, the galaxy build up. But, you know, there's so many things that, you know, we're going to be looking at. The peak of galaxies formation is around 3 billion years after the Big Bang at redshift 2. And it's going to be dramatic to see the information we're going to get in galaxies there. So, yeah, you know, I think the excitement is going to be pretty periodic and repeated.
Okay, let's ask more questions.
You mentioned that the lifetime could be as long as 20 years just for the fuel.
Yes.
So what else limits the lifetime, in particular that active cumulative is fixed?
No, that's interesting. You're correct. So that is the only, so there's a mechanical system there at the present. Those cryocoolers have been astonishingly reliable on Hubble and they've been used on other missions. This one is the sort of more challenging one to have built and test and so on, but it could last a significant fraction of that time. Instruments, you know, things can happen with instruments, but the detectors on the infrared detectors are much less susceptible to damage from cosmic radiation than CCDs are, which have typically been used a lot in the past. So the detectors, I think, will last a long time. So, but you know, when the project manager, when, you know, we sort of iterated on this, how good the burn was, he said 20 years, something else is going to go wrong before we run out of fuel. Yeah, he's probably right, actually, having watched Hubble and so on. So, you know, things happen, and there can be radiation hits on electronics, which can do some damage. And we have, you know, everything is duplicated, and we have capability to upload software and replace and enhance or change capabilities. So, yeah, I hope we really get, you know, 15 years, and it'd be great to get 20 out of this.
And what's the scale of the annual operations internationally?
In what?
In dollars, or?
Oh, so the operations budget is probably, if you throw in the GEO, there must be about 150 million, 180, something in that ballpark. You know, Hubble is running around 90, so, and this has got a larger science budget element in it, so I'd say around that level.
Appreciate it.
Thanks, Garth, it's great. 20 years is fantastic.
Yeah,
I was
it's
thinking
good.
about that. One of the really wonderful things about Hubble is that how broadly it's been used by the community. And I'm wondering how you see this developing into JWST. You know, I think there's some, you know, some things that are more technically challenging or less accessible for people. Do you think that will change over time, or how do you think that will go in terms of the breadth of use?
You know, I think the proposal process is more challenging, largely because we wanted to be able to turn around much more quickly than we do with Hubble. It takes a long time between doing the proposal and Hubble and getting the data. Excuse me. We wanted to make that shorter. So the proposal process is trickier, but I think people learn very rapidly. And I think the first tack was, you know, the results from that were very good. And a lot of young people, a lot of new users came in. So I'm very optimistic about this being, you know, really across the community and getting a lot of support, interest, and having them, young folks as well as, you know, sort of more regulars involved in this. And double-blind selection process is clearly changing that. I heard the other day that 30% of the new proposals for Hubble under double-blind are now new users. So this is good. You know, folks who, you know, who might before have a little trouble having visibility within the normal TAC process with double-blind, where it concentrates on the science and what you're going to do with it, has really helped younger people or people who are not as connected, as it were.
Roger. So the limited size of fairings at the time this was all put together drove a lot of the decisions that were made.
Yeah, right.
This is an era that seems to be passing. are we ever going to do anything like this again?
Oh, I think we could certainly do,
Well, why would we ever do anything like this again?
well, we want to do a 15-meter to detect Earth-like planets. No, I think we can, deployable telescopes, I think, have been demonstrated. This one is particularly challenging because of that sun shield. If you have a warmer telescope and you have a simulated sun shield, it would be very much easier to do. And I don't think there's much, let me back up. Originally, we did talk about, we want 8 meters. The only way we could think of launching that was to have a special big fairing bill. But once it got into the 90s and it was understood that the companies were launching classified missions with deployable, using deployable capabilities, we thought, well, why don't we do the same thing with this? It turns out that our deployments are trickier than any of those, like mostly radar, I think, off the radio wavelength missions. So the constraints were much less. But, I don't know what else is going on with the classified missions. I have no idea. They could be doing, deployments like this as well. But I still think this is probably one of the most challenging missions ever launched, classified or unclassified. There's a lot of, very hard technology in here. And sun shield deployment, I still sort of wake up and go, we deployed that thing and there wasn't a problem. Because having seen it, we think there's so many moving parts there and all this flimsy plastic, but it worked. But having done that, we can clearly do it again. I'm pretty optimistic about doing, even bigger missions in the future. I suspect it won't quite be in my lifetime, knowing how long these things take.
Yeah. Is there anyone on Zoom with a? I'm not seeing any chat.
Well, can you click on the chat?
If you maybe you could click on the chat, maybe you've got something.
Yeah.
40 messages.
Sorry, 40 messages. Okay. Okay.
Oh, I can't hear.
Yeah. Oh. Yeah, this is very weird. I have a very weird Zoom screen, and I don't seem to have any control over anything. I just have 4 little windows. Can you get the chat up? Right.
It's not coming up on the screen.
No. Yeah, this is very weird.
Here's that question.
Sorry?
Question next.
Question. Oh, while we're waiting, question.
So I was quite surprised to see the 1990 decadal survey recommend a 6-meter UV optical infrared telescope. It's awfully similar to the recommendation of the 2020 decadal survey. Do you have any thoughts on that, or what the next generation space telescope might be, or what you'd like to see?
Yeah, so let me say something. So in 1990, the decadal survey has an Uber committee that is the one that makes the final choices, and then it has panels that feed into that. So the panel made a recommendation, and the Uber committee said, no, we don't want to do that. This, you guys are not ready or whatever. And we really want to do Spitzer and some other programs. So that was what they decided. So it was part of the process, but it wasn't recommended formally. So interestingly, you jump to 2020, so they say 6 meters, but it's a very different 6 meters. One, it's warm, but 2, it has absolutely exquisite and demanding performance on its optics, because it's going to do coronography and try and detect Earth-like planets around stars. So you're now trying to suppress the light of the star by 10 billion times, and that's not easy. So while it looks like it's similar, it's actually a very different and far more challenging mission in many ways. And that's why they were talking about it being $11 billion for a mere 6 meter, so, which is warm.
Look, we're a quarter of an hour over. We started late
Yeah.
with technical problems, and I'm very sorry to those on Zoom that we don't seem able to access the chat. We're not
I
able to
think
see
if
it.
you stop sharing, you'll be able to see the chat.
There's a lot I'm worried about the time. So what I'm going to propose is, those who are on chat, we'll see if we can access that, and we'll finish the colloquium now because we're 15 minutes over. And those who are still interested in seeing the chat questions, we'll try and address them straight after this move. So let me just ask you to give a round of applause to Garth. And then we'll try and get on to the chat and come down to the front if you're interested in hearing the answers to the chat questions.
Yeah.
Maybe you stop sharing now.